Design of a thermos. A thermos will help you understand the benefit of double-paned windows. If you look into a modern thermos, you will see a shiny liner. The outside layer is usually stainless steel or plastic. What you can't see is the space between the two layers. What special material insulates that space? Nothing. When the thermos is made, the air between the two layers is removed. Then the layers are sealed so nothing can get back in. We call this sealed, empty space that contains no particles of air or anything else a vacuum. Why would a vacuum be the best insulator? A vacuum has no particles to transfer energy between the liquid in the container and the surrounding environment. Energy can still transfer by conduction through the thermos lid and the walls of the container as particles of liquid transfer energy to the particles of these solid parts. But the vacuum layer slows the rate of overall conduction. Take note. Think about conduction, which is energy transfer by contact between particles. Write down your ideas about why a vacuum affects conduction. A thermos can keep soup hot or juice cold. How? Inside is a double-walled container. The space between the walls is a vacuum. Nothing, no particles. The vacuum reduces energy transfer into or out of the container. Inside a thermos. Liquid cocoa. Inner liner. Outer plastic shell. Surrounding air. Vacuum layer. Decreasing conduction. Let's go back to the window. Particles of glass in a single-paned window rapidly conduct kinetic energy from the warm side to the cold side of the pane as particles within the pane collide with each other. Double-paned windows have a space between two layers of glass, like a thermos. The space between panes is not a vacuum, however. Windows need to be strong and watertight. The space between panes is filled with a substance that has very few particles spread out over a lot of space. What substance meets this criterion? Hint: think about solids, liquids, and gases. The space in most double-paned windows is filled with a very stable gas, like argon, Ar. Some windows are filled with krypton, Kr. Using a gas between two thin panes reduces conduction and provides better insulation than a single, thicker pane. So engineers have developed a good solution: the double-paned window. Does that mean they will stop coming up with new ideas? No. Engineers are always improving designs. They are now designing triple-paned windows for even better insulation. Your class developed an insulating design in just a few days. Imagine what you might find if you kept testing new designs. Energy transfer through windows accounts for about 25% of heating and cooling costs for the average home. The gas layer in a double-paned window cuts down energy transfer by conduction. Cross-section of a double-paned window. Heating the atmosphere. The campfire has burned down to a bed of hot coals, perfect for toasting some marshmallows. You get a stick about 1 meter m long to keep your hand away from the hot coals. After a minute, the marshmallow is brown and gooey. You pop it into your mouth. Yikes! You didn't wait long enough for it to cool. This story has two intense experiences with heat. It shows two ways that energy can move. 1. The coals heated your skin from a distance. 2. The marshmallow transferred energy directly to your tongue when you tried to eat it. Energy transfers 3 ways: convection, conduction, and radiation. Which do you think is at work when embers toast a marshmallow? When a freshly toasted marshmallow burns your tongue? Energy transfers. Objects in motion have kinetic energy. The faster something moves, the more kinetic energy it has. Particles are always in motion. They vibrate back and forth in solids and move all over the place in liquids and gases. The amount of kinetic energy in the particles of a material determines its temperature. In hot materials, particles are moving fast. In cold materials, they are moving more slowly. Conduction. Kinetic energy naturally transfers from a hotter location to a cooler one. In our story, the energy in the hot marshmallow transferred to your tongue. This memorable experience is an example of what happens when energy moves from one place to another by direct contact. That kind of energy transfer is called conduction. The faster-moving particles of the marshmallow transfer energy to the slower-moving particles of your tongue. If the particles of your tongue gain too much kinetic energy, you feel it as pain. At the same time, particles of the marshmallow lose kinetic energy. The marshmallow cools off. Another example of conduction is when you jump into a cold lake and energy moves from your body to the water. Brr! A painfully burned tongue is a one-way transfer of energy from hot marshmallow to cool mouth. Blowing on food before biting can help by increasing energy transfer to the surrounding air. A particle in a hot material with a lot of kinetic energy collides with a particle in a cold material with little kinetic energy. Energy transfers at the point of contact. The cold material particle then has more energy, and the hot material particle has less energy. Radiation. What about that energy from the hot coals, which you felt from a distance? That energy traveled right through air without any direct contact. That is called thermal energy, which is a form of radiant energy. Radiant energy can travel in rays straight from sources like the hot coals, light bulbs, and the sun. Rays from the sun travel right through the empty space between Earth and the sun. Some of the sun's rays are visible light rays. Some are invisible, such as infrared rays, beyond the red end of the rainbow, and ultraviolet rays, beyond the violet end of the rainbow. Heating the atmosphere. Our atmosphere heats up by these same two kinds of energy transfer, radiation and conduction. Starting with radiation, visible light rays from the sun pass right through our atmosphere. They strike Earth, get absorbed, and heat up the land and ocean. The heated land and ocean come in contact with air particles. That conduction transfers energy to the air. Infrared rays from the sun are a different story. Many infrared rays travel through the atmosphere like visible rays do, and heat the land and ocean. But some infrared rays don't make it all the way to Earth's surface. They get absorbed by gas particles in the atmosphere. Gases that can absorb infrared rays are called greenhouse gases. Carbon dioxide and water vapor are both greenhouse gases. When they absorb infrared rays, they heat up the atmosphere. Remember the heated land and ocean? These warm materials radiate thermal energy as infrared rays. This is very important. Greenhouse gases absorb these infrared rays, just as they absorb the infrared rays coming directly from the sun. The atmosphere heats up more. Greenhouse gases. Greenhouse gases have earned this nickname because they trap thermal energy in Earth's atmosphere. Here is how that happens. The greenhouse gases in the atmosphere, including water vapor and carbon dioxide, absorb infrared rays, heat up. They re-radiate the thermal energy in all directions, including back toward Earth. Say an infrared ray was headed away from Earth, perhaps after being radiated from a hot asphalt schoolyard. It could be absorbed and re-radiated instead of leaving the atmosphere. The more greenhouse gas there is, the more likely this is to happen. Some of the solar radiation passes through the atmosphere, and some is trapped in the atmosphere by greenhouse gases. The effect of this is to warm Earth's surface and the atmosphere. The greenhouse effect. Without any greenhouse gases, Earth would lose a lot more thermal energy to space. Earth's average temperature would be about 33 degrees Celsius, degrees C, colder than it is. Compare this to the Moon. There, the temperature ranges from 123 degrees Celsius to negative 233 degrees Celsius. Average, negative 55 degrees Celsius. Because there is no atmosphere, all the thermal energy from the day radiates back into space during the night. By comparison, greenhouse gases keep Earth at a warmer, stable temperature that permits life. Energy gets around. So visible light rays and infrared rays heat the surface of Earth through radiation. In addition, energy transfers to greenhouse gas particles in the atmosphere when they absorb infrared radiation. This radiation is not absorbed by nitrogen and oxygen particles, which make up most of the atmosphere and are not greenhouse gases. But all gases in the atmosphere heat up when they come in contact with the heated surface of Earth. The energy transfers through conduction. In addition, greenhouse gas particles that absorb infrared radiation can transfer energy to nitrogen and oxygen particles through conduction. Energy continually transfers between Earth's systems due to interactions among our planet's air, land, and water, as well as living things. Atmosphere. Air particles are warmed by conduction. Hydrosphere. Water vapor particles in the air are warmed by radiation coming up from Earth. Geosphere. Earth warmed by solar energy radiates infrared radiation. The final piece of the puzzle is convection. Convection moves masses of air or water, both fluids. At the hottest parts of Earth's surface, huge masses of air heat up, expand, get less dense, and move upward. This starts up the largest convection cells on Earth. Over the ocean, large amounts of heated water vapor rise, riding along in the giant convection cell. When the air cools, water vapor condenses into droplets of liquid water, forming clouds. Convection cells redistribute thermal energy and water around the planet. Take note. Explain 2 ways that Earth's atmosphere gets heated. How do greenhouse gases help keep Earth warm? Record your ideas in your notebook. A typical coal-burning power plant releases 3 5/10 million tons of carbon dioxide into the air every year. Greenhouse gases and climate change. Greenhouse gases help keep Earth warm. This affects humans and other organisms on Earth. If we change the amount of greenhouse gases, are we changing the amount of energy in the atmosphere? One greenhouse gas that humans regularly produce is carbon dioxide. It is released every time we turn on a gasoline-powered car or burn coal to generate electricity, among other sources. If you imagine all the electricity and gas used by each of us in industrialized nations every day and multiply that by the number of people, well, you can imagine why the amount of carbon dioxide in the atmosphere is increasing. Scientists have tracked carbon dioxide in the atmosphere since the 1950s. The data are shown in the graph. Scripps Institution of Oceanography, NOAA, Earth System Research Laboratory. Atmospheric carbon dioxide at Mauna Loa Observatory. Parts per million, ppm. Year. About 1/4 of greenhouse gas output comes from burning fossil fuels for transportation. Wind on Earth. What's the weather going to be like tomorrow? If it was cloudy to the west yesterday, are the clouds likely to head toward you or away? Can prevailing winds help you forecast the next day's weather? Remember the airflow pattern that you observed in the convection chamber. A candle at one end of the chamber heated the air. Cool, smoke-filled air entered the chamber at the other end. It immediately sank to the bottom of the chamber. The cool air moved across the bottom of the chamber and under the warmer, less dense air. It lifted the warm air. The rising warm air had no place to go, so it traveled across the top of the chamber to the other end. There, the air cooled and sank. The whole cycle repeated, producing a small convection cell. This is a miniature model of what happens in the atmosphere. You have seen that Earth materials heat and cool at different rates. Remember the experiment with sand, soil, water, and air. You also drew diagrams of local winds to show how this differential heating creates convection cells that cause wind. Wind is a major weather factor and also moves weather systems. Some types of severe weather are classified by wind speed. Hurricanes have winds of 119 kilometers per hour or greater.
In ancient times, sailors realized that certain winds are always present at certain locations on Earth. In fact, many sailors became rich by using the trade winds to travel from one city to another. Why do we have these winds on Earth? Welcome to Moo Math and Science and Global Winds. In order to understand global winds, we need to learn some basic facts. Due to how the Earth tilts on its axis, the sun's rays strike the Earth at different angles. This results in unequal heating of the Earth's surface. For example, the equator receives more direct sunlight than places such as the Arctic Pole. This is why the equatorial region is so much warmer than the Arctic and Antarctic poles. Cold air is denser than warm air. It sinks, creating high-pressure areas. Warm air is less dense and rises, creating low-pressure pockets. Air will always flow from high-pressure areas to low-pressure areas. Because the Earth spins, anything that floats above the Earth's surface, such as air, appears to follow a curved pattern of movement. This is called the Coriolis effect. The Coriolis effect heavily impacts the travel pattern of global winds. In the northern hemisphere, air moving from north to south deflects to the left. From the equator to the poles, air deflects to the right. Now let's put all this together and look at some global winds. First, we will label the Earth. The direction of the global winds change every 30 degrees on Earth. You can see I have the Earth labeled 90, 60, 30, and 0 degrees in the northern and southern hemisphere. At 90 degrees, the air is very cold and dense and creates a high-pressure system. At 60 degrees, the air is warmer, resulting in a low pressure system. At 30 degrees, the air is cooler than it is at the equator, creating a high pressure system. It is very hot at the equator, and the warm air creates a low pressure area once again. Notice the alternation between high pressure and low pressure areas. Every 30 degrees witnesses a pressure change. Next, remember that the Coriolis effect heavily impacts airflow. Wind systems will twist clockwise or counterclockwise under the Coriolis effect. In fact, this is what happens with the prevailing winds. There are three main prevailing belts: the prevailing westerlies, the trade winds, and the polar easterlies. The polar easterlies are the dominant winds found between 60 degrees of latitude and the poles of the Earth. Remember that air likes to move from high pressure areas to low pressure areas. So the wind will start from the poles at 90 degrees, areas of high pressure, and move down towards 60 degrees where the pressure is low. The prevailing westerlies are the dominant winds found between 30 and 60 degrees of latitude, and the Coriolis effect moves them from west to east. Hint: winds are always named from the direction that they start from. The trade winds will move from the high pressure area of 30 degrees towards the equator, which has low pressure, also called the tropical easterlies because they blow from east to west. Are there areas with little wind? The doldrums, also called the intertropical convergence zone, are such a place. At the equator, the air is very warm due to direct heating from the sun. Remember, hot air rises, and since the equator receives such intense sunlight, the air at the equator rises vertically like a hot air balloon instead of blowing horizontally. As a result, the doldrums, which are located between 0 degrees and 5 degrees of latitude, experience very little wind. The horse latitudes are located at 30 degrees north and south, also experience little wind. The horse latitudes are areas of high pressure, and thus winds go separate ways from one another, searching for pockets of low pressure. The prevailing westerlies will head towards 60 degrees of latitude, while the trade winds will head towards the equators. Sailors have tried to avoid areas like the doldrums and the horse latitudes because they wanted strong winds that would push their boat along.
Global convection. Now let's look at differential heating on a global scale. Because of the high solar angle, Earth's surface is always warmer in the tropics, the part of the planet near the equator. Tropical land masses and water masses in the tropical ocean absorb a lot of solar energy. Air in contact with the tropical sea or land receives a lot of energy by radiation and conduction. Huge masses of air heat up and begin to rise. The largest convection cell on Earth starts here. It is the size of the entire equatorial area. The equatorial convection cells circle the globe like two bicycle inner tubes. Because much of the energy transfer occurs over the ocean, large amounts of water vapor rise high into the atmosphere, riding along in the convection cells. The convection cells that surround the equator are the largest on the planet. Equatorial convection cells. Land and ocean in the tropics absorb a lot of solar energy, causing them to heat up. Air above the land and water heats up, then moves upward in the atmosphere. As the warm, moist air rises, it cools. At about 10 kilometers km altitude, the warm air has cooled to the same temperature as the surrounding air. The cool air begins to fall back to Earth. But because a wall of warm air is rising from the tropics, the cool air cannot fall back directly. The cool air, still at about 10 kilometers, flows north and south like two gigantic conveyor belts. When it reaches about 30 degrees north and 30 degrees south, it descends toward Earth's surface. Meanwhile, the warm, low-density rising air in the tropics creates a low-pressure area. The cooler, more dense air that is descending from the upper atmosphere creates a high-pressure area. The more dense air flows into the area of low pressure to replace the rising air. This creates a huge convection cell called a Hadley cell, named after George Hadley, 1685 to 1768. He proposed the idea of these enormous convection cells in 1735. The bottom of the cell flows across the surface of the planet, from about 30 degrees north and south toward the equator, producing wind. This diagram is another way of looking at the convection cells shown on the previous page. It shows the airflow at the equator from a different perspective, from a position at the surface of Earth. Can you see why winds in the tropics typically blow toward the equator? Model of a Hadley cell. Wind. 0 degrees. 10 degrees. 20 degrees. Prevailing winds. Differential heating creates high and low pressure areas, causing wind. Winds always tend to move from a high pressure area to a low pressure area. However, winds do not blow directly from high pressure areas to low pressure areas. Instead, the wind curves. Why does this happen? As air in the atmosphere moves, Earth is rotating, dragging the air along with it and changing its direction. This is called the Coriolis effect. This easterly movement of the surface of the planet means the winds in the Hadley cell do not go straight north or south. The Coriolis effect causes the winds in the northern hemisphere to curve clockwise, and the winds in the southern hemisphere to curve counterclockwise. The combination of high and low pressure areas and the Coriolis effect controls the prevailing wind direction. Prevailing winds are global winds. They are predictable for different latitudes on Earth. These global winds are not greatly influenced by structures on Earth's surface, like forests, cities, and mountains. Prevailing wind direction is important to people sailing ships, flying balloons around Earth, piloting airplanes, and building wind turbine farms to generate electricity. As you will see later, prevailing winds are also an important factor in the local weather. Winds of the world. Centuries ago, sailors named the different prevailing winds. Between 5 degrees and 25 degrees north or south latitude, dependable winds usually carried a ship across the ocean quickly. Because ships were crossing the ocean carrying goods to trade between the Americas and Europe, these winds became known as the trade winds. Near the equator, the air is rising. At about 30 degrees north and south latitudes, the air is descending. At these latitudes, the wind is usually very light or non-existent. Sailing ships in these areas could get stuck for days or weeks. The calm area around the equator became known as the doldrums. The windless area around 30 degrees north was known as the horse latitudes. This term might have been coined when Europeans were carrying horses across the ocean to their colonies. Ships would sometimes get stuck at about 30 degrees north latitude, making the trip much longer than planned. The sailors would run out of water for the horses, and horses could die. Prevailing winds and Hadley cells happen at the surface of Earth. There are winds at upper levels of the atmosphere as well. The most familiar one is the jet stream. Jet streams are narrow bands of high-altitude wind that occur in predictable patterns but vary over time. Changes to the jet streams can greatly affect weather patterns on the surface of Earth. They can even change the flight time of aircraft. Flights from the west coast to the east coast typically take less time than the other direction because they are boosted by the jet stream's airflow. In addition to the Hadley cells, the northern and southern hemispheres have two other bands of convection cells. They produce prevailing westerlies, wind blowing from the west, between 35 degrees and 55 degrees north and south latitudes, and polar easterlies, wind blowing from the east, north, and south of 60 degrees. Prevailing winds impact weather and climate by moving heat and moisture in predictable patterns over Earth's surface. Prevailing
And the wind is blowing from behind you. The wind will push on the sails and your boat, which is attached to the mast, will be propelled forward. No mystery there, right? But what about when the wind blows towards you or from the side? You'd think it'll be impossible for you to move forward, right? Well, think again, because not only will you go forward, but set your sails right and you can sail even faster than the wind. So how do sailboats work and sail into the wind? Short answer, your sailboat is actually an airplane on its side, and your sail is one of the wings raised vertically. When sailing, the sailor will adjust the sails so the wind pushes on the inside of the sail, keeping it stretched tight, but also at an angle so some of the wind passes along the outer side of the sail as well. This is exactly what happens on wings of an airplane. The pilot controls the angle of attack, so some of the wind pushes the wings up from below, and some of the wind, by following the curvature of the upper part of the wing, pulls the wings up as a result of the Coanda effect and Newton's third law of motion. This resultant force is called lift, and lift is what keeps airplanes flying and sailboats sailing. However, unlike the wings of an airplane where the direction of lift is vertical, in case of sails the direction is horizontal. But that's not the end of the story, because a keen observer will have noticed that the direction of lift created by the sails, while horizontal, is at an angle to where we actually want to go. We're missing something here. Well, no need to look far, because the secret sailors like to call the keel is hidden right beneath us. Remember that a sailboat is actually an airplane on its side. The sail is one of the wings and the keel is the other one, hidden underwater. When lift from the sails tries to move the boat at an angle, the water, which you can think of as much denser air, pushes on one side of the keel and pulls from the other side, creating lift. In this regard, keels are no different from sails or wings. However, unlike wings of an airplane which create lift in the same direction, up, the wings of a sailboat creates lift in different directions, both at an angle from where you want to go, which individually would be unhelpful. But when the effects are taken together, the result is the forward propulsion we were looking for. And that's how sailboats work and sail into the wind. Except for the no-go zone, which is about 45 degrees on either side of the wind, where it's physically impossible to create lift no matter how you angle the sail. You obviously need
Local winds. Local winds change with the season and even with the time of day. They are the direct result of local differential heating. Local winds are affected by land structures and bodies of water near land masses. A typical Chicago weather forecast in the summer might go something like this. Sunny skies today with a high of 29 degrees Celsius inland. Temperatures will be in the low 20s lakeside. Chicago's climate is affected by its location near a large body of water. Land masses near the Great Lakes or the ocean feel the cooling effects of the nearby water. From your experiment with heating earth materials, you know that the land gets hotter faster than water when the sun shines. The hot land transfers energy to the air above it, and the air expands. The warmer, less dense air creates a low-pressure area over the land.
It's a sunny day at the beach. As the sun rises, the land warms up faster than the water does. This causes the air above the land to also warm up. Warm air, being less dense, expands and rises, leaving an area of low pressure. Meanwhile, the air over the ocean is cooler. Cooler, denser air sinks over the water, creating an area of high pressure. The differences in pressure and air temperature create a convection current. Warm air over the land is replaced by cool ocean air. This air is warmed by the land and rises, and the cycle continues. Winds that blow from the sea to the land are called sea breezes. At night, the convection current reverses. After the sun has set, the land cools more quickly than the water. Therefore, the air above the land also cools down. Cool air, being more dense, presses down over the land, creating an area of high pressure. Meanwhile, because water cools down slowly, the air over the ocean is still warm. Warm air, being less dense, expands and rises, leaving an area of low pressure over the water. At night, cool air over land moves towards lower pressure over the ocean. This air is warmed by the water and rises, and the cycle continues. Winds that blow from the land to the sea are called land breezes.
Even though the sea also absorbs energy, its temperature does not change much at all. During the day, the sea stays cooler than the land. Less energy transfers to the air over the water. It remains cool and dense, which means higher air pressure. Air from the high pressure area over the water flows into the area of low pressure. Wind blows from the water onto the land. This is called a sea breeze or offshore breeze. A cubic meter of warm air has fewer particles than a cubic meter of cold air. Warm air is less dense than cool air. This convection current creates wind that blows from the ocean to the land. Sea breeze. Air. At sunset, there may be a period of calm when land and sea temperatures are about equal. After sunset, the land cools off quickly. The air over the land cools and contracts, becoming more dense. At this point, the local high pressure area is over the land. Meanwhile, the sea temperature is still about the same as it was during the day. So the air pressure is about the same, but it is lower than the local pressure over the land. Now the local high pressure over the land moves into the lower pressure area over the water. Wind blows from the land out to sea. This is called a land breeze or onshore breeze. This convection current creates wind that blows from the land to the ocean. Land